In thinking about an abstract data type, we try to think about what it is we'd like to do with the abstract data type and what its behavior should be. This is very much like the object design that we've done before. So without thinking about a specific implementation, let's just think about what we would do with any kind of a list that we had in front of us. Well, we need to be able to add things to the list. Perhaps we'd like to find the nth thing in the list. What is the third thing I have to do today? I might want to find out where something occurs in the list. When am I supposed to eat today? Is that the fourth thing I do or the fifth thing? And I might decide to remove something from the list either because I already did it or because I no longer need to do it. Finally, let's suppose we want to find out how long a list is to get an idea of the work that might lie ahead of us. Now, the idea is that no matter how a list is implemented, we should be able to perform these operations to any kind of a list. Specific implementations may differ as to how they implement the operations, but the operations themselves would always be offered to the end user. So let's first define the interface, and then we'll see some specific instances of using it. The syntax for doing this in Java is to declare an interface instead of a class. Here we see public, and instead of the word class, we use the word interface. We call it list, and we're going to parameterize it by type t, like we've seen before. T will be the type of thing that's held inside the list. When we design this particular list, we don't know what exactly the end user has in mind for the contents. It might be a list of colors, it might be a list of integers. We can be abstract and generic about that by including the type parameter t for list. Now notice that an interface has no constructors. It's not really a class. It's defining the signatures of the methods that will be in a class, more like the promise of what is to come, but it is not itself a class. And therefore there's no instance variables either, because it offers no actual behaviors, just the descriptions of what those behaviors would be. So we fill in the interface by simply adding the signature of every method we want anything that implements this interface to offer. Back to the things we decided a list should be able to do, we decided we should be able to add something to a list. So we think about the ability to add something to a list by adding a method called add, ADD, and we don't know the type of the thing, but we have a type parameter that allows us to be abstract about that. So the signature is add, and we take in something of type t, and we can give the variable name of the parameter anything we like. Here it's just called e for element. Now for a list, this is always going to return true because adding to a list is always a successful operation. We might see later, for example, that adding to a set depends upon whether the element is already in the set or not, so its add might return false. But for a list, we expect to have true returned. We want to be able to get the ith element in the list. Now, as is typical with Java and most programming languages, I is going to start at 0. So if I say get of 0, it's going to return the first thing in the list. Get of 1 would return the second thing, and so on. What is the type of the returned element? Well, we don't know specifically, but we have a generic idea of it as being type t. So the signature for this method is t, that's the return type, and the name is get, and we specify the element order, the element number that we'd like to get from the list as I. We want to find out where a given element occurs in a list. For that, we provide the index of operation. We provide the element e of type t to index of, and it will return the first occurrence index of that specific element in the list. So if my list consists of eating, studying, and then eating, and I look for eating, eating occurs first in the list, so index of on eating would return 0, because remember 0 would be the first thing in my list. We want to be able to remove something from a list, and there's two possible ways of thinking of that. Maybe I want to remove the first occurrence of eating from my list, in which case I could specify the element e of type t, and I should look for that element and remove the first occurrence. Or maybe I decide the third thing in my list ought to go away no matter what it is. So there are two signatures for remove, one that accepts an element and one that accepts an index. In the case where it's an index, we can return the actual element removed from that index in case it's of use to the end user. So the return type of remove with index specified is actually type t. Finally, we want to be able to compute the size of a list. And that's going to return an integer, but needs no information taken in. It simply returns the size of the list. In my example of eating, studying, and then eating, the return value for that particular list would be 3. So these operations, and actually many more, define the abstract data type of a list for Java. It's simplified here to just the bare essentials in terms of our coverage, but if you look online, you can certainly find all the other methods that are offered by list. So the interface defines the signatures of the methods we want. It's basically saying what we can do, but not how it's implemented. There's no instance variables, there's no constructors. It's basically pure design without any implementation. Now, why do we do this? We do it so someone else can come along and offer alternative implementations that could satisfy the interface. Why do we need more than one implementation? Often these offer trade-offs in terms of efficiency, and some implementations will be good in some cases and others for other cases. An implementation that comes along and implements the interface actually says in its public class statement that it implements the interface. It has to have all the actual methods for the methods in the interface to be instantiable, and if any are missing, we can't really use the object. So for list, what implementations exist? It's easy to see these online, but let's talk about two of them. ArrayList is one such implementation, which implements a list as an array. Each of the elements we add to the list is placed into the array in succession. Now, inserting into an array, suppose you want to insert into the middle, is relatively awkward because you have to move all the elements down to make room for the new element that you're inserting. So an array list would be a good choice if the list is relatively fixed. For example, suppose you're creating a list of all of America's national parks. That's not something that changes very frequently, and deletion is rare to non-existent. So for a list that's relatively stable and relatively small, an array list is a really nice choice. A linked list, whose implementation we study later, grows and shrinks very easily. It uses links or chains between its elements, and so insertion and deletion are relatively easy. Imagine inserting a link into a bracelet where one is broken. We can simply put it where it needs to go without disturbing the rest of the bracelet. So an example where a linked list would be useful, consider a line of people waiting to ride a roller coaster. Now mostly this list is growing, but it grows frequently. People come into the line because they want to ride the roller coaster. Now occasionally someone in the middle may get cold feet and drop out because they're scared or because they don't want to wait. So removing is also an operation that we might want to do occasionally. In this profession, in the profession of computer science, choosing the right data structure becomes a very important task. It's not something we cover very much here. It's more in a course on the analysis of algorithms. But here we can appreciate the fact that there is more than one implementation that can implement a given interface. How do we actually instantiate a linked list? A common way to declare it is to use the generic or abstract data type in the declaration. So here we see list of string, and we call the list eating. And on the right-hand side of the equal, we say new linked list, because that's the implementation we actually want to use of string. On the right-hand side, we cannot say new list of string, because list is an interface, not a concrete or instantiable class. So the right side has to assign some type that matches list of string. Linked list is one such implementation, and so is array list. If we have the linked list constructed and received by the variable eating, we can then start to use it. Here you see us adding strings to this linked list. First we open our mouth, we insert food, we chew twice and swallow, and this is basically a recipe for how to eat a meal. When we print this out, we should see those elements in turn. You're next going to try implementing this, and then you'll try using the same operations on a set.